Right. Hey, everybody. We are talking clustering, and specifically today we are working with k-means, which is it's kind of our bread and butter clustering algorithm. So we'll learn k-means first, and then in anomaly detection, we'll work with another clustering algorithm called dbScan. So let's jump right in. What is k-means? So what? Why should you care? And then what do you do with k-means? So the first thing out of the gate, k-means is an unsupervised machine learning algorithm. So all of our clustering is unsupervised. That means we don't have foreknowledge. We don't have labeled data. We don't have answers. And where this might come up in places outside of exercise sets, but on the job and on new data sets, is getting to know your data a little bit more deeply, right? Instead of thinking of 3 or 4 variables at a single time, if the clusters say these things are similar, it makes sense to look at that cluster and see if there's something there, right? The best case scenario, in my opinion, is when your k-means clusters, they have an identifiable meaning in English, and you can then use that identifiable meaning in English to help you out with a whole bunch of other tasks like data exploration, dimensionality reduction, and even to make better models, better predictive models. So what's going on with k-means, and why is it called k-means? K is a variable, right? And we've seen k before with k nearest neighbors. So in both of these cases, k is up to you, okay? Just like the k in the interquartile range rule, that's also up to you. So it's a variable, it's a user-specific number, and you do need to specify k ahead of time. That's not going to keep you from cranking out a bunch of k-means in a loop to test k at 1, 2, up to whatever you think is reasonable. And there's no guarantee that our clusters have the same number of points. That's really dependent on the distribution of the data itself across the multiple columns. So what are some pros? What are some cons of k-means? So we'll start with the pros. K-means is relatively fast compared to other clustering algorithms. The idea of cluster centroids, think of that as the sort of center of a cluster. That idea is very interpretable. And it is one of the most common clustering algorithms. There's others out there, but k-means is really a bread and butter kind of workhorse. Some things that we need to keep in mind, our data should be scaled before we cluster, unless for some reason all of our variables are in the exact same units. So if you have 4 columns that are all in millimeters, you don't need to scale anything, right? But when we have one column in millimeters, another column in millions of dollars, another column in number of bathrooms, we have to get a sense of scale. Specifically so we don't overweight or underweight certain features, right? If something was priced at $1.5 million, that would be because of the magnitude, that it would take more precedence than coefficients in a predictive model. So always scale your numeric columns, and you'll need to encode your categorical columns as well, your binary or your categorical columns, because k-means is all distance based, right? Yes, question from V. Okay, cool. I see. Okay. Hey, Kate.
Thanks, V. Yeah, can you dig in more on why, just because it's the same units, they don't need scaling? Because kind of my understanding was the magnitude was very important. So if we have something that happens to be 5 miles long, but only 0.2 miles thick, is that not important to note, even if they're in different columns? I don't know.
Well, yeah, what I heard in there was you used the same unit of measure for both, right? The thing is units of measure. That's really the big deal, and also the removing the units themselves and replacing back in, like take a min-max scaler. instead of whatever your range of numbers are, your numbers go from 0 to 1.
But we could still have something that has, the same units and the magnitude is, 1,000 magnitudes different, and that I thought would still have the same distance issues between columns or features than.
We completely hit the reset button on magnitudes when every value in the entire data set is between 0 and 1. And it's almost as if we're normalizing our units. Maybe not normalizing is a good term, but we're taking the units away.
I know, I guess that makes sense, but you just said we don't have to do that if the units are the same. So you said only scale if the units aren't all the same. Is that right?
Yes, that's what I'm saying. Yes. Yeah, if you've got the IRIS data set with 4 columns of millimeters, you're just wasting time.
Okay.
But if you've got miles in one column, feet in another column, pounds, price in Bitcoin in another column, we should be scaling all of our stuff all the time with clustering, or the results are going to be bananas. They won't even make sense. Did that clarify, or am I on the same page as you?
I'm still confused, but sometimes my brain just gets stuck, so I'll have to ruminate on that.
I'm going to refer you to the potatoes lesson, the potatoes lecture from Mr. John Salas, if y'all were in the room for that one. Cool. So we scale before using k-means, and the scale can have a huge impact, right? If we think of one column having millions of dollars and another column having millimeters, we don't want the sense of scale of the millions of dollars to overwhelm things. So that's why we're really getting like relative scale when we use a scalar. Another con of k-means clustering is it's highly susceptible to the curse of dimensionality. So let's do a pop quiz. What in the heck is the curse of dimensionality, and why should we worry about that? Fred?
When you have more independent predictors, like you have more dimensions, and it's something that's in space that adds like just more weird calculus into it, so it screws up like the distance ratio.
Yeah. The more it's almost like a kind of a law of diminishing returns. Kind of the more columns you add to your data set, the less we can believe the predictions based on that. And there's a second hit from curse of dimensionality, and it's usually the one that you feel first, and that's the computational complexity expands exponentially. Imagine if the number of columns you have is an exponent. Things are going to grow real fast. Like square or cube is an exponent. Yeah, it means we're going to have a lot of math going on, a lot of computation. So there's 2 things going on with curse of dimensionality. The first is based on the number of data points and columns you have coming in, your amount of computation is starting to grow, not just linearly, but exponentially, right? Like a cryptocurrency 2018 curve, right? Where it just goes straight up. Yeah. It's an issue in a lot of ML. Mm-hmm. Yeah, this isn't unique.
Okay.
But this is a twofer. So our curse does 2 things. It costs more to compute, but then the meaning of each new column that we add starts to decrease in its ability, in its explanatory ability. Yeah, I think, go ahead, Fred.
Is that expressed in terms of error, or is it expressed in terms of like overfitting the model on your training set?
Where that's going to express mathematically is, I realize this is not a coefficient regression-based model. It's distance-based, but really the problem is measuring distance starts getting more, you can measure it, but the meaning of each new dimension muddies the water is the best. So that's the analogy, but where does this occur in the actual math? It is going to occur in the coefficients. So think of a linear regression. You have a coefficient for each variable coming in. So if you have like an X, a Y, and a Z to predict A, so if you have some regression that's X, Y, and Z, it's a multiple regression, and you're trying to predict A or something like that, you'll get 3 coefficients like 0.5 out of your model, 0.3 and 0.2. Now there's not a magic number for cursive dimensionality, but 3 is a pretty happy number. These all add up to 1, so all of your coefficients are going to add up to 1. But what if you had 1,000 columns? Your coefficients mathematically have to sum to 1. But the more columns you have, each one will have less and less impact and influence. And so if we have, so the sum of all of these needs to equal 1. If we have 1,000 columns, the coefficients keep getting smaller and smaller and smaller, which means our ability to understand the importance of those gets smaller and smaller and smaller. So it's not that our ability to measure a hypotenuse between points is more challenging in higher dimensions, but the real reason of having interpretable coefficients, like human beings want coefficients because we can say, oh, X must be a bigger contributor. But if we have thousands of columns and we don't know what's what, yeah, this can get especially gnarly if you encode a lot of categoricals here, because like each categorical is a 0 to 1, where each continuous could be 0 to 1, but it's not a binary. Like it's 0 to 1 after you scale it, but it's not a binary. I wish I had a clear crystal answer like 20 columns. It's just not that cut and dry. It has to do with degrees of freedom. It's also a function of how many data points your data set has. But it is a curse. It is a curse of dimensionality. And even if we solve the computational part, we still have some other issues. Yeah.
I know this can vary tremendously, and maybe by
Sure,
industry
sure.
or anything, but typically on the job, most of your, let's say that interquartile range of the amount of projects you're doing, how many features do you think you're dealing with typically?
I mean, the answer is it depends, but like when I think of my own domains, where I've applied these tools to solve problems for CODA, right? Not just doing curriculum development, not just doing authoring exercises, but like doing a security audit, right? Or something like that, or even building marketing personas. It's in the dozens. We've had one internal project that was north of 300 columns, but that was really, we were trying to make a kitchen sink data set. And HubSpot wanted to give us a kitchen sink data set. Even if we only cared about 10 columns, we could only export it with everything. So, but usually a couple of dozen. Yeah. Like if you're looking at logs or anything security, you'll have much more data, but like less columns. Demographic data, surveys, they get up there. Like if you're doing like working for Forrester Research or something like that, they'll have a lot richer qualitative data sets usually.
Like financial.
Oh, sky's the limit. Yeah. And any kind of financial modeling I've done, it's not hundreds, it's barely dozens, but depending on what you're trying to do, you might need a sophisticated model. Yeah. Yeah, any other follow-up on that, or? Yeah, that's definitely will vary by domain, but also like what you can have access to, right? Just because you got some chops doesn't mean HR is going to give you all HR data, right? I'd say HR data has lots of columns. Finance does too, yeah. Kind of related to the scaling business. is K-means is sensitive to outliers. So let's jam about this a little bit. And these are all kind of related, right? Imagine if you had 3 columns. Now I'm asking you to imagine something. Let me see if I can annotate here. Let's say we had an X, a Y, and a Z. But X was a continuous number from 0 to 1. Y is a continuous number from 0 to 1. And Z is a binary, 0 or 1. Almost immediately, your categoricals, they're not necessarily outliers because we can't go higher than 1 on a min-max scalar or a binary. But by its very nature, the binary columns, the categorical columns introduce extremes, right? So keep in mind your K-means algorithm, anything that's distance-based is very sensitive to outliers. So if something is way over and just in another state, right? It's gonna throw things quite a bit. Okay, so let's keep going. Any questions, comments so far on the pros, cons of K-means, situating the context? Yeah, Fred.
Recommend using scalar because not sensitive to outliers.
I like min-max scalar personally. Because any outlier handling, this is just a me thing. I want to handle the outliers rather than the scalar handling the outliers. Because then I can point to the logic, whether if it's I came to a conclusion or I used interquartile range rule. Like, I guess if you're in a hurry, you can use a scalar that handles outliers. I prefer not to. But yeah, just a couple of outliers can really move your centroids around. Cool. All right. Let's start talking about the algorithm underneath the hood of K-means. This is actually not the most complicated code in the universe. We still want to use sklearn's library, so we have the same API. We don't have to build it ourselves. But we'll start with our data and we'll randomly choose K points. So the random here is, it's not like pure math definition of random because it's coming from a computer, right? But we'll start with a random number of points, K. So if you say hey K-means make me 3 clusters, we get 3 random data points. Those 3 random data points are called the centroids. And what the algorithm is going to do is calculate the distance from every point in the X data set to each of the centroids and assigns each data point from the data frame to the closest centroid. Pretty simple so far. Now, this isn't going to be perfect. We reposition the centroids such that they are the average of all of the points assigned to them. This is kind of an iterative process. And then we repeat starting from step 3 until a condition for stopping is met. And the defaults are pretty good there. But I'll show this to y'all visually real quick. Let's see. Maybe there's a thing. Animations. Oh, here we are. I'm going to steal from one of my colleagues. What we're looking at is the process of a K-means algorithm. It starts by generating K number of random points, assigns incoming data points to those centroids. Let's take this from the top again. So the first thing we get is we get the data frame, right? That's what all of those little pepper flakes are. And then the algorithm randomly chose 3 data points. That's what these X's are. Notice, I'm going to direct your attention, these data points are not optimized in any way. They're random and their initial positions are garbage, most likely. we see in the data, it kind of looks like there's 3 clear clusters already. But let's see what happens. So k-means assigned the green, the blue, and the yellow to those 3 data points because each one of these data points was closest to that specific centroid, right? So far, so good? Or do we have questions so far? This is like step 1, 2. Step 1, dump out all the Legos. Step 2, choose random points. The number of random points is the value k, and then we will get the data points that have the lowest amount of distance to that centroid. We call them a cluster so far. And check this out. Y'all saw the centroids move. This is an iterative process, iterative like iterate across an array. The new position for these centroids is the geometric center of those data points. And then we run through that process again, see how some of those blue data points that used to be closer to the blue centroid now belong to the yellow centroid. This iteration process means that we are reaching a consensus. I'll hit that again. You dump out all your Legos, you randomly choose 3 starting points. Move your centroids to the center of those 3 clusters and then iterate. In the defaults, let's take a look at the defaults here. If you don't specify number of clusters, it'll default to 8. So you have to specify the number of clusters. This max iter, that max iteration has to do with looping. Well, what is iteration? Well, maximum number of iterations of the k-means algorithm for a single run. So what we saw with that animation, we saw an iteration of like 2, maybe 3. So underneath the hood, this iterative process of repositioning the centroids and trying to get a better class, a better center, a better definition of center is what's going on here. And you can certainly crank up your max iterations. I think 300 is totally fine. I think that's a good default. So I would accept just about every default except for the number of clusters, because that's going to be a problem if you have 5 features, right? Or not necessarily a bug, but you don't want too many clusters. Well, I'll send that out to y'all. So that's how k-means is working. Underneath the hood, it's an iterative process. There's some randomness involved. And we have 2 pieces of vocabulary. Centroid, that is one of the cluster centers. And there's another vocabulary term that's going to help us a little bit later when we decide how to determine k, and that's inertia. And inertia is the sum of the square distances from each point to its assigned centroid. So it's not really error because these aren't predictions, but this is telling us just basically how much distance there is between all the data points in the assigned centroid. Let's take a look at the code. We pull in we're pulling in the Iris data set. Iris data set has a couple of columns. I don't need to scale these because they share the same measurement already. And we have the species name. So let's see what we can work with here. Folks, we can cluster only on numeric columns. So if you wanted to cluster on something that's categorical, you've got to encode that. So in this space, we're clustering just on petal length and sepal length. And like everything else in sklearn, the modeling is the easiest part. Make the thing, fit the thing, predict, use the thing to make predictions. So here's what we get. We say, hey, k-means, make me a k-means object. Then we fit to our training data, or to our X rather. And then we'll make predictions. Now, k-means' predictions are going to be integer numbers, 1, 2, 3, 4. If you say 5 clusters, You get five numbers, 1, 2, 3, 4, 5, 2 clusters, 1, 2, right? So what we're doing here is we are making a prediction of the cluster. K-means.predict gives you back that prediction number. And then we can plot this out. So by making the cluster number its own column, we could then visualize the original data on the upper right-hand side, breaking out by actual species by the hue. And then in the lower right, the K-means cluster, check out the legend right there, the 0, 1, 2, those are the cluster numbers. And isn't that interesting that some of the clusters just so happen to line up with species? And I see a question from D'Angelo. Go ahead, D'Angelo.
Yes, I did have a question, but I think by looking at this chart, it was able to be answered. I was just wondering why they had, you had 2 features, but you had 3 clusters. And I was just wondering why was that, but I see that you do have the original one here as well.
Yeah, like we could send in a K of 10, but a K of 10 is going to find like a cluster here in the upper right. A K of 10 may force this lower cluster into 2 or 3 clusters instead of 1. That's kind of the challenge of a higher number of clusters than necessary, is because the K is being enforced by the algorithm, it will force you to have that many clusters.
Okay.
So my guidance on that one is less is more.
But what about the contrary? What about having less features? So 3 clusters, right? So when you have like, let's say 1 feature, like, how does it work that out?
Oh yeah, let's say we only had 1 feature, right? Like height, right? Just 1 feature. You could have, if the data supported 4 clusters, you could basically you're binning in that space, right? Yeah. Did that answer your question, Lincoln? D'Angelo, any other?
Yes.
Cool. Yeah, Lincoln had a follow up there, and I see Kate's got a question. Go ahead, Kate.
Yeah, is there any requirement on number of points per cluster?
Number of points. Let me see. I don't think so.
And so they don't have to be the same or anything. It's just going to choose the ones that are closest. One cluster could have 5 points, the other one could have 50.
Yeah, like the initial centroid locations are almost always going to be garbage, but this iterative process is what realigns them to what is essentially the actual center of that cluster. There is a challenge though, if we set K too high, like this demo looks really cute and clean, but that's because the K is 3 and there's 3 reasonably visible clusters, right? But if our K was 5, we would have 5 different centroids out here vying and competing for data points to belong to them. And so that's one of the risks of that's the upside risk. But really, I haven't seen a limit on the number of data points or a requirement. Like I wouldn't do K-means if I only had dozens of observations, but hundreds, I'm feeling better. Thousands, I'm feeling even better. Cool. So just because K-means can be really dang valuable in making clusters that could also overlap with another variable, right? These just happen to have quite a bit of overlap, don't they? Like the lower left cluster and the lower left cluster and both. So K-means did not take into account that species information, but if we encoded the species, the K-means would take that into account as another dimension. It's pretty cool. Once we train our model, once we fit the model, so you make the thing, you fit it, and then you use it to make predictions. We have a couple of other things we could ask about from that K-means object, from that fit model. We could call the attribute cluster underscore centers underscore, and we'll get the location of each cluster of that centroid, if that's useful for us, if we wanted to plot things out. Like that's how the X's were plotted out in this animation, was talking to the K-means object. to get the location of them. And then labels underscore gives us the labels for each observation. And then the inertia is the sum of squared errors from each data point to its associated cluster. We'll talk about that in just a moment. So our cluster centers can have an X, a Y, a Z, however many dimensions you sent into the cluster, into the clustering algorithm. And let's take a look at how we can make a data frame out of those cluster centers. We can say, hey, pd.dataframe, hey, k-means, give me basically the latitude and longitude centers of each cluster, whatever your columns are, right? Give me the center of that, and then specify the column names, because the cluster centers don't know their names, to be x.columns. And if we could plot these centers out if we needed to. Right, if we were to group by the cluster, we could get aggregates. Now, this is really interesting. By having a cluster, you have another way of aggregating your data. And how useful is it for us to do things like control for one variable if we can group by it or plot by it, right? So the cluster centers aren't data points themselves, but they are the calculated average of that entire group, right? So what we're viewing right here is a fully trained k-means algorithm. This X in the upper left is part of the legend. It's not a fourth K. And these are all distance-based, and it ends up being pretty useful, right? Because even if you didn't have species, we're getting groupings that are meaningful based on those two variables, the petal length and the sepal length. That's pretty cool. Let's talk about exploring different numbers of K. This is really the biggest downside for k-means is what do you set your K at? And how do you decide that? I'd say if you're going to do any clustering, start with 2. So you at least have 2 groups. And what we can do here is one of 2 things. You could either make a whole bunch of clusters manually. What this example is doing. We have 2 clusters of petal length and petal width. And we could crank K up. Now, in this case, K is 5 on 3 different species. So while each cluster is pretty, well, some of these clusters are well defined, like the blue, like this whole other section is 4 different clusters. So we'd have to really look at the variables and run them like a dot describe on everything else. See what's not accounted for in this visual, right? Because only petal width and petal length are accounted for in this visual. We want to see if anything else is similar. So this might be too much. It's kind of a Goldilocks problem. So how do we solve the Goldilocks problem? We use something called the elbow method. So we're going to choose K by means of using inertia. So again, inertia is the sum of squared distances from each point to its centroid. So it's not error, because there's natural variance in data, right? But what this elbow method does is it shows us the trade-off between inertia and the number of K. So what we're looking for with this elbow method is like an elbow on an arm. We will look for the point where adding additional clusters doesn't give us as much of a large reduction in inertia. So we're going to start with 2 and go to 12 for K. And let's take a look at our 2 extremes. When we go from a K of 2 that has quite a lot of inertia, inertia is not a good thing here, right? When we go from 100 something inertia to 50 inertia, the slope of this tells us that going from 2 to 3K is helpful. This nice steep slope tells us that that's helpful. The slope changing from 3 to 4 to basically like 45 degrees southeast this is helpful, but it's not as helpful as going from 2 to 3. Now let's look at the other extreme. What if we go from a K of 10 to a K of 11? Well, our inertia went from like 17 to 15. It wasn't that big of a deal, right? So there's not a hard and fast, just like everything in the whole dang field, there's not a 45-degree angle, 30-degree angle on your inertia here, because that can change with the scale of your x-axis and y-axis. But really here, you're looking for an inflection point that might make sense. So looking at this, 10 or 11 doesn't make sense to me. 9, 10, 11, 8, 7, 6. I'm really thinking the sweet spot here is somewhere between 3, 4, maybe 5, maybe 5. So this is like a lot of other stuff. This is a judgment call.
So is this perhaps still using the iris as
Yep, it is, let's see. Yeah, it's fitting on X. So it's fitting on only on 2 features. Those 2 features were pedal width, these 2, pedal length and supple length. And so let's go back to another example real quick. I talked about inertia, one of our new vocabulary terms. It's the sum of the squares of all of the distance. So we've seen squaring distance and we've seen summing that before. So if we were to take the distance from every orange point to the centroid, square it, and then sum it, plus the sum of squares, the sum of all the square distances on the green centroid plus all the sum of square distances, right? Why do we square? To penalize things that are farther away. And what that'll give us is a single number, just like RMSE is a single number, right? So plotting out your Ks, the slopes of these will be different based on different data sets, right? And there's distributions within those data sets. But this going from 2 to 3, just how steep that is tells me that 3 is a better K than 2. The steepness of 3 to 4 tells me that 4 might be better than 3. I give it like a 50-50 chance. But going from 4 to 5, I'm still going to do that and see what the data shows. But once that inertia starts to flatten out, you're getting diminishing returns. And in fact, you run the risk as inertia gets lower and lower and lower. Take a look at this 5 cluster here. Inertia is great on that 5 cluster. But other than the setosis down here, is this actually predictive in its power? This is too many K, especially since we only have three species. So, there's no hard and fast rule that the number of categorical outcomes in one column determines your cluster. But sometimes it could be that easy. Sometimes you could be that lucky. But in this case, we know that there's some misclassification between Versicolor and Virginica. They overlap right around here. But so sometimes a larger K is good, sometimes it's not. But this chart right here just ripped the code right off to plot the elbow method.
So knowing kind of what the distribution is, like plotting the actual species versus that clustering, you interpret that like clustering. It's kind of like not vague, but like a problem.
Yeah. Okay, good. Yeah, you may find that some of your clusters make perfect sense and 1 or 2 of them are gibberish. In that case, either bump up your K or crank down your K, or you may have an artifact where you have 4 clusters that are great and 1 that's garbage, and changing your K undoes that work of the positivity. Let's see, what else do we have for you? Okay, perfect. So again, there's not a magic solution, but basically once your inertia starts to flatten out, you're getting less and less benefit for each new K. We've got some code in here for reminding y'all for plotting out different colors for your centers, for your clusters rather. I'm pretty partial to Seaborn myself. If you set Seaborn hue equals cluster or column equals cluster, you'll get a color for every cluster or a column for every cluster. And you can combine that with another categorical variable and learn quite a bit about your data. So there you have it, folks. A little bit of k-means clustering. It is a wonderful tool to try to get to know the relationship between your variables when you have like too many variables to fit on one chart. Right? And we'll talk about, I think I'm completely confident we're going to make it to the using clusters lesson this afternoon. Because I want to talk to y'all about how to use the model output, not just how to do the modeling, because doing the modeling is 3 lines of code, right? Make the thing fit the thing, use the thing to make predictions. But we'll work on these exercises, and then in the afternoon, we'll get into the using clusters. So these exercises themselves will work with the IRIS data set for the first one, and then crank out a model on the mall. And then we have an exercise for you to compare the results of clustering unscaled data versus clustering scaled data. So there's some experiential learning for y'all involved here. A little bit of a bonus if you feel like going above and beyond. And of course, the real MVP is using any extra time on your project. Cool. Let's take a little break. Y'all have certainly earned it. I'm gonna stop the screen share here. And we'll see you after the break.